right, today we will be talking about rotation of a rigid object about a fixed axis, which is chapter 10 of Zerway and Jewett. So firstly, we have our angular position, velocity, and acceleration, which we need to define, because otherwise without this definition, we won't be able to go along. And it's very similar to their linear counterparts, angular position. So first, to represent the position of P, we will be using polar coordinates r and theta. So r will be the distance from the origin to P, and theta will be measured counterclockwise from a reference line. So as we will look in figure 10.1 from Zerway and Jewett, at the very top you have the circle with the origin, and then your point P, so r is that distance. And then as it rotates, we will measure counterclockwise, as you can see with this arrow, and to get our angle theta. Now within this, we can also figure out the arc length of this, which is the distance around the disc travels, by multiplying the distance r from the origin to P and times theta, or vice versa if we don't know S. If we don't know theta, but we know our arc length, we can just divide our arc length by our radius to get our theta. Next, we have angular velocity and acceleration. Much like linear speed and velocity, we will be using the average position, delta theta, and the average time, delta t, to find the omega average. As you can see within our first equation in the top left, omega average is equal to the change in theta, so theta final minus theta initial over time final minus time initial, so delta theta over delta t. Whereas we can also get an instantaneous angular velocity, just like we can get an instantaneous linear velocity by doing the limit as the time approaches 0 for delta theta over delta t, or just the derivative of the time derivative of theta. And much like with angular velocity, with our angular acceleration, we have our same exact thing, except we just changed the thetas with omega. So you have omega final minus omega initial over the time final minus time initial, or delta omega over delta t, to get our average acceleration. And our instantaneous is just doing the time derivative of velocity, of the angular velocity. And we also have our kinematic equations for a rigid object, which very much like to their linear counterparts, they're the exact same. So if you remember the particle under a constant acceleration equation, you first start with, you've got your final velocity is equal to your initial velocity times your acceleration times time. It's the exact same equations. All we're doing is switching out the velocities for omegas, the A's for alphas, and the X or Y positions for theta. And we also have a way to translate between the two quantities. So the velocity is the time derivative of the arc length, which is equal to r times the time derivative of the angular position. So and d theta, and the time derivative of theta is also omega. So therefore, we also have velocity is equal to the distance r times the velocity times the angular velocity. And that's how we can go back and forth, and we can do the same thing with acceleration, but changing out the thetas for omegas. So the time derivative of velocity of velocity is equal to r times the time derivative of the angular velocity. So the transiential acceleration is just the r times the angular acceleration. Now, for centripetal acceleration, we have a little bit different. So we also have velocity squared over r squared, or r times omega squared. It's all the same stuff. It's pretty simple. Now we also have the torque and the moment of inertia of a system and rigid object. So first we have our torque, which is just our distance times the force times sine of phi, or F times delta D, or D. Our moment of inertia, where M is the mass and Mi is the mass and Ri is the distance from the rotational axis. This is how we calculate the moment of inertia of a system of particles. That's why it's Is versus the Io, where it's just the integral of where r is the distance from the mass element, dm to the axis of rotation. We also have different types of rotational kinetic energy, power, work, and total kinetic energy. So rotational kinetic energy, defined as K sub r, is equal to 1/2 times the moment of inertia times omega squared. Then we have our power, which is just our torque times our angular momentum, or angular velocity. And our work, which is equal to 1/2 the moment of inertia times omega final squared minus 1/2 omega moment of inertia omega initial squared. And our total kinetic energy is going to be 1/2 times the moment of inertia times omega squared times 1 plus 1/2 times the mass times the velocity squared. I hope you all have enjoyed this video. Have a nice night.